All right. Thanks, everyone. Do you see my full screen or do you see my notes?
We see, I see your notes, yeah.
Okay, let's swap. I never know. So this should work better. All right.
Oh, it's beautiful, right.
Okay. All right, thanks everyone. Good morning, good afternoon, good night, wherever you are. And thanks for joining this seminar. I hope I can give you a 20-minute, 25-minute, maybe kind of taste or appetizer of the work that we're doing in our research group. Our research group is called the Ice Sheets and Climate Research Group at the University of Colorado Boulder. I'm an assistant professor there since 2017. And we have a really cool, exciting research group of 6 graduate students, 2 research faculty, some undergraduates from time to time, and myself. And we do work on the interaction between mostly the Antarctic ice sheet, which we all share our passion about, and the atmosphere as well as the ocean surrounding the ice sheet. So I'll highlight basically 2 main topics out of the kind of spectrum of research topics that we work on today. So just a periodic reminder that ice sheets, including the Antarctic ice sheet, are losing mass in response to recent climate change, and they're contributing to sea level rise. And I want to show this this figure and animation to all of you, not because I think you don't know this, but just to give you an update or kind of where we are in terms of ice sheet mass balance. What you see here on the left is a map of the Greenland ice sheet, on the right, the map of Antarctic ice sheet to scale. So you can see how much bigger Antarctica is compared to Greenland. And in the middle, there's a time series there. And I'll show this again so you can look at it. And as the time series evolves from 2002 to the present day, to last summer, you can see that the colors change on the ice sheets, which means that the ice sheets are changing mass. Reddish means losing mass, blue means gaining mass. Overall, the ice sheets are losing mass. This is not a surprise again. Greenland is losing more mass than Antarctica, about twice as much. But also, if you look at the spatial signature, that's really interesting because Greenland basically loses mass everywhere around its periphery, as you can see here. I'll show my cursor here. Do you see? Can you see my cursor? I hope so.
Yes.
So you can see it's basically all around the ice sheet, while in the Antarctic mass loss is focused on the Amundsen Sea embayment. And this also really shows the different drivers of ice sheet mass loss. On Greenland, it's mostly the impact of the atmosphere that raises atmospheric temperatures, that increases surface melt, and in response, the ice sheets is losing mass through surface meltwater runoff, while the Antarctic ice sheet mass loss is focused in space on the Amundsen Sea embayment, where ice shelves are in contact with warmer ocean water that is getting warmer in time. Ice shelves are losing mass, are thinning, disintegrating, and that leads to a response of the grounded ice sheet in terms of increase of ice discharge across the grounding line and ice mass loss. So this kind of illustrates or kind of makes the point that Antarctica is driven mostly by ocean warming, or Antarctic mass balance is driven by ocean warming. And that's true to a large degree, but what we are interested in as a group mostly is kind of seeing Antarctica as the part of the climate system. So not only the ice-ocean interactions, but also interactions between the ice sheets and the atmosphere and the ocean, and seeing the ice sheet really as an integral part of the climate system, which I think is the way forward. But we have a lot of trouble kind of matching our climate models to resolve that ice sheet in that coupled climate system. So the ice sheet mass balance is the rate of ice change or mass change per unit time. So if you weigh the ice sheet at time 0, and you do it again at time 1, the difference in mass divided by the difference in time between 1 and 0, that's the mass balance. So mass balance by itself is a change of mass in time, which is sometimes confusing to people. So we're looking at how the ice sheets are changing mass in time. And mass balance is typically expressed in these units of gigatons per year, which is nothing else than mass per unit time. And the ice sheet mass balance itself is a balance of different processes, many processes actually, but we can summarize them as the surface mass balance, which is the sum of the surface processes and ice discharge. So the mass balance is the difference between those two. If SMB is larger than discharge, mass balance is positive, which means the ice sheet is gaining mass in time. And the opposite is true for negative mass balance, which we are currently observing from GRACE, as I've shown you in the first slide. What I will focus on, and with what we are focusing on as a group, is mostly the surface processes part. So kind of the input term of the mass balance equation. And on the Antarctic ice sheet, we can summarize surface mass balance as something that involves a lot of processes, including redistribution of snow on top of the ice sheet driven by katabatic winds. We have sublimation, mass loss from snow at the surface. We have interactions, obviously, between the ice sheet and the atmosphere in terms of radiation, albedo, clouds, long wave and short wave radiation, turbulence, and so forth. If we go down onto lower portions of the ice sheet, we start seeing surface melt. And this is the part 1 that I want to talk about today. And then, of course, the ice sheet interacts with the ocean. And I want to talk a little bit at the end about kind of some really preliminary work we're doing on that front. So part 1 will be on ice shelf firn, and I'll talk about what firn is. And part 2 will be on ice-ocean interactions. So part 1 is about surface melt, and we think about Antarctica as a really cold and dry place, which is true for many parts of Antarctica, but still close to the coasts at the low elevations, we find summer melt occurring in summer. And this is super important because summer surface melt creates liquid water, and liquid water in turn affects properties of the surface and the near surface. And this is really important for ice shelf stability, as I hope I will explain to you in the next few slides. So we think, again, about Antarctica as dry and cold. And this is what we kind of started with when we studied East Antarctic ice shelves. But when we arrived on one of these ice shelves and we drilled a fern core, we saw liquid water in that fern core, and we actually lowered the camera inside a borehole, and this is what you see here. This is a subsurface lake on an East Antarctic ice shelf at 30 degrees east, something like 72 degrees south. And it's a subsurface lake of 4 meters deep, 1 kilometer across, itself buried 4 meters under the ice surface. So we didn't know these bodies of liquid water existed until we went into the field, and we realized that these kind of water bodies exist and are plentiful all around the ice sheet. And there are many other surface melt phenomena or liquid water phenomena on ice shelves. We found fern aquifers, for example, recently on West Antarctica. And why is this relevant? Again, it's relevant because ice shelves are super important for Antarctic ice sheet stability, and ice shelves can become vulnerable as a result of surface melt processes. So I use the term gatekeepers of Antarctica for ice shelves. Ice shelves are super important as they buttress the ice upstream from the grounded ice sheet. So ice shelves are important for ice sheet stability and basically mitigating, buffering Antarctic mass loss as a response to climate change. Now, these ice shelves themselves are also vulnerable to climate change. We see that they are vulnerable to ocean warming, as I discussed, but they can also become vulnerable to atmospheric warming. And this is due to in response to the surface meltwater loading, essentially. So typically, a firn layer, so the firn layer is the in-between product between fresh snow and solid ice. The firn layer consists of ice particles or snow particles, and in between those crystals, we see airspace, and that air is there to potentially store and retain liquid water. So this is what a healthy, typical firn layer looks like, or should look like, on an ice shelf. Ice crystals with airspace, pore space in between, and that pore space, if there is surface meltwater at the surface, will be able to refreeze and retain that surface meltwater, typically in the form of ice layers, but it can also be, for example, subsurface water or firn aquifers or other hydrological phenomena. Now, if we move to a warmer climate, on the right side in panel B here, we'll see that the firn pore space is no longer there to retain the water. There will be melt ponds at the surface. Those melt ponds exert vertical pressure onto the ice shelf. The ice shelf can fracture from the surface all the way to the bed. This is kind of an extreme example, but this is what we call hydrofracture. This is hydrofracture from liquid water at the surface all the way to the underside of the ice shelf, and that can lead to catastrophic, very extreme, very fast disintegration of ice shelves. Now, this is an extreme example, but we know that this has been observed already, which I will show in the next slide. Now, the question is, when will this firn become saturated on Antarctic ice shelf, potentially leading to hydrofracture? So when we will move from panel A here to panel B, depending on the climate change that we're projecting into the rest of the 21st century. Now, coming back to this hydrofracture, this is an example of hydrofracture in reality. The Larsen B ice shelf, and again, most, if not all of you are aware of this extreme case, but this is end of summer 2002, so almost 20 years ago now, and 2002 was a really warm summer in the Antarctic Peninsula. So this is the northern side of the Antarctic Peninsula. It's just, the northern side of Antarctica, the warmest side. And in a matter of a few weeks, from end of January to mid-March, you can see that the Larsen B ice shelf completely disintegrated as you follow from left to right and top to bottom. Now, if you focus on this upper left image and you kind of zoom in, you can see something like this. This is actually an image from a bus airplane flying over the Larsen B ice shelf. And you can see that these blue spots here on top of the ice shelf, these are essentially these melt ponds that we were talking about. So this is the melt ponding at the surface, and that led in part at least to the disintegration of the Larsen B ice shelf, now only almost 20 years ago. As the Larsen B ice shelf disappeared, we saw an increase of ice flow into that former ice shelf basin. So the upstream glaciers actually accelerated in response. So this is exactly what we are talking about as the loss of the gatekeepers of Antarctica in action. Now, this is a very small ice shelf, and it's on the northern side of the Antarctic Peninsula, the warmest side again. So the question is, when, if ever, will this occur on other sides of Antarctica? So what we will do here is use this CESM2 Earth System model and force the atmospheric information from that CSM2 model into a very sophisticated snow model or firn model, which essentially resolves these processes from the transition from fresh snow to solid ice, as well as the processes involving surface meltwater production, infiltration of liquid water, retention, loss of airspace, and things like that. So we'll look at different scenarios, the historical simulation, and then 3 projections of 21st century climate change in the CESM2. Now, what does a firn layer look like? Well, these are 2, again, extreme examples of a healthy firn layer and a less healthy firn layer on the left and on the right, respectively. And what you see here, and if you're not familiar with this, I'll try to clarify. So 0 here means we're at the ice surface, at the ice shelf surface, and we're going down in depth. So we're basically drilling inside the ice shelf, and we're looking at how the density of the snow or firn product changes with depth. And that's what is shown here. So you can see typically the surface is pretty low density, pretty fresh, lots of air in between the ice crystals. And as you go down, there's more and more compression of that airspace. The airspace is basically compressed out of the firn, and we ultimately end up with solid ice, or even more than solid ice if there are ice layers in between. So in this left example, the firn layer we would assume is around 20 meters thick, because the ice density is reached at around that level of 19 or 20 meters depth. And the other, anything below is ice. In the right example, we actually see an ice layer very close to the surface that is very thick. So the firn layer is only very thin, because you can expect water to basically, this ice layer to be impermeable for water. So any water that infiltrates from the surface will only be able to infiltrate maybe a couple of meters, and then be ponding on top of this ice layer, which is impermeable. So in this case, the firn layer is pretty thin. Now, another term that we want to use is so-called firn air content, which is basically the vertically integrated amount of pore space or airspace that is available in the firn. And you can see this, or use the metaphor of Swiss cheese, which also contains pores. This is a solid ice of Swiss cheese, which is our firn. Now, if you would basically melt the Swiss cheese, the air would be out of it, and you take the difference between thickness of the original one and the melted one, and the difference between the two, that's the firn air content. It's the total vertically integrated depth of air within the firn, if that makes sense. So a lot of air means a lot of pore space available for retention, for refreezing. A low number means a very unhealthy firn layer, maybe something that looks like the one on the right side. Now, this is the present day situation. Now, let's go to Larsen B ice shelf here, which is just north of the Larsen C. It's no longer there, but you can see a Larsen C that the firn air content is very small. There's not a lot of air content in the firn. That makes sense, because it's an unhealthy firn layer. We see on Larsen C a lot of ponding as well, a lot of ice layers. So this makes sense. Anywhere else on Antarctica, we see very high values, right? Lots of air in the firn. This is an example, or this is a signature of very healthy firn. This is good, because this is firn that can retain a lot of surface meltwater. Now let's move to the end of the century, and what you will see is not entirely surprising, but a little depressing, is if you project the climate change throughout the 21st century and apply it to our firn model, you'll see that in a low emission scenario, we start seeing spots with low firn air content on the larger ice shelves, the Ronnie, the Ross, as well as the Amory ice shelf, as well as some other ice shelves. But there are many areas that still have high firn air content, including most of the ice shelves along the West Antarctic ice sheet, which is due to a lot of snowfall in winter, which basically keeps this firn layer pretty healthy. Medium emissions and high emissions is much more depressing, much more lighter colors, which means lower firn air content, which means a higher risk for things like hydrofracture. Again, I'm not saying this is happening. It's showing the vulnerability of ice shelves to atmospheric warming in a sense. And there are many other factors that contribute to ice shelf disintegration. And this is how I see Antarctica evolving, Antarctic ice shelves evolving as some sort of, as some sort of analog to what Greenland looks like right now. Remember, Greenland had this 2012 extreme melt. Well, we can still see this 2012 surface if we go down a little bit, a few meters, in the firn on Greenland. And that 2012 surface acts now as an impermeable layer, which means that the firn layer, instead of being very thick, is now only a few meters thick. And this is exactly what I think is going to happen on many ice shelves, especially in high emission scenarios. Now let's take a zoomed out approach now and look at what the SMB in general looks like in CESM2. And I think this is a really, I think, underappreciated thing in the community, is that we always think about Antarctic surface mass balance as precipitation driven. Precipitation increases with climate warming. And that's true. That's true for many parts of the Antarctic ice sheet. And it's also true in the CSM2 results. So we can see a 21st century time series of the grounded ice sheet. So this is only the grounded ice sheet, surface mass balance integrated. And you can see that SMB increases with time and increases more with high emission scenarios, which means that it's, this is the typical Clausius-Clapeyron idea of higher temperatures, more snowfall, higher SMB, which mitigates potentially dynamic mass loss. Well, that's true for the grounded ice sheet, and this is important. But the other side, the other world, is the ice shelves, where instead of increasing SMB, we see a pretty constant SMB until 2060, 2070, and then SMB starts decreasing in the medium and high emission scenarios. And this is exactly driven by, instead of increasing snowfall, we see increasing rainfall, we see increasing surface melt in response to increasing atmospheric temperatures. So the future SMB on Antarctica feels like it's a tale of two worlds, the grounded ice sheet and the ice shelves. And again, the ice shelves are important as being the gatekeepers of Antarctica. And looking from a more ice dynamic perspective, and this is a result from a recent paper by Rob de Canto and colleagues, which some of you I'm sure are aware of. And this shows now ice sheet modeling results. So this is using SMB as a forcing, and then look at the dynamic response of the Antarctic ice sheet, including ice shelves, right? And what I want you to focus on is this red line, which shows the rate of global mean sea level rise from Antarctica. So this is nothing else than basically mass balance, right? Or mass loss, I should say. So as it increases, mass loss increases. So this is a scenario with 2 degrees global warming by 2100. Now look at this 3-degree global warming and look at the difference between left and right. This is just 1 degree more of global warming. And you can see now, instead of a linear increase, we see a very strong exponential and kind of sudden increase, as if some sort of threshold has been reached. Well, this threshold is exactly the same threshold as this one. It's because ice shelves are becoming unstable in response to atmospheric warming, leading to hydrofracture, ice shelf loss, and the ice sheet responding in terms of a very strong increase in mass loss. And again, this is just one model. This is a model that is subject of a lot of discussion, but it's a result that shows how important ice shelf stability is to the Antarctic ice sheet. Now, the question is, what happens in this scenario to, the next question is, what happens to this scenario, to the freshwater fluxes from the Antarctic ice sheet? And what happens to the Southern Ocean in response? And that's part 2. And I'll really fly through this because I don't want to use too much time. Because you can expect, as the Antarctic ice sheet loses mass, there is an increase in freshwater fluxes into the Southern Ocean that might have an impact on the ocean circulation. sea ice conditions and so forth. And this is shown already by many studies. For example, this one which shows another climate model and shows that the SSTs globally respond to an increase in freshwater fluxes from Antarctica. And mind you, this is something that is not resolved by climate models. By default, climate models assume that the ice sheets remain in equilibrium, remain in mass balance. So this is something climate models do not know unless you tell them to do it, which is something we've done with CSM2. So we've had a control simulation in blue where the freshwater fluxes remain constant, which is like an unlikely scenario in any case, but we want to see the sensitivity. And then we have this so-called IMBY simulation, which is driven by the GRACE observations, which you've seen in the first slide, until 2020. And then we kind of use this 3-degree scenario. So we see a pretty constant signal until 2060 or so, then a sudden increase afterwards, driven again by this ice shelf loss. And we want to understand the impact of the increase in freshwater fluxes by just comparing these two simulations, if you will. And again, this is very preliminary work. This is just a couple of weeks old. So we're looking into the results right now. But some interesting first kind of findings is if we compare the two simulations in blue and black. So blue is the increased freshwater simulation, the black is a control, with the observations of sea ice extent in the southern hemisphere. We see some interesting idea that we kind of move towards the observations. You know, we're not there entirely, but it seems like, especially from the spatial signature, we see that our increased freshwater simulation looks a little bit more like the observations. Again, we want to run more ensemble members. We want to understand if this is just noise or an actual signal in response to the increase in freshwater fluxes as observed. But if so, we can, at least from the CSM2 perspective, we can at least try to attribute some of the observed variations and trends in southern hemisphere sea ice to the increase in freshwater fluxes from Antarctica. Now, if we move towards the rest of the 21st century, we see that this IMBY simulation remains higher than the control for the rest of the century. And then really, as soon as this freshwater flux really ramps up, it basically remains constant. The sea ice extent on the southern hemisphere does not decrease anymore, which kind of doesn't make sense if you think about the increase in warming. So the world keeps on warming in the simulation, but the southern hemisphere sea ice does not decrease anymore. And at the end, in 2100, it's actually higher than all of the large ensemble simulations in the CSM2 model. So the large ensemble uses SSB 370 forcing, which is a lower forcing than what we're using. But despite that, we have a higher southern hemisphere sea ice extent at the end of the century. So we have a higher warming, but we end up with a higher sea ice extent, which is interesting. It seems like the Antarctic freshwater kind of dominates the global warming signal in terms of the southern hemisphere sea ice, at least. So that's really interesting. We're kind of exploring the physical processes by which this happens. We see a sudden increase in Fresnel ice formation in the model in response to the enhanced freshwater fluxes. But we're going to look into this in a lot more detail in the next few weeks. So to end here, take-home messages: the impact on fern is really important. And this kind of comes back to the workshop that we wanna organize next year, because fern is super important. It's super important for Greenland, but also for Antarctica. Atmospheric warming saturates the ice shelf fern, and that enhances the risk for surface-based ice shelf collapse or hydrofracture. And those collapsing ice shelves potentially accelerate Antarctic ice loss, and that has an impact on southern hemisphere and global climate potentially. And this is something we're looking into right now. So thanks so much for listening, and happy to take and answer any questions.
Thank you, Jan.